And so in this next section, in essence, what it allows us to see is how the equations that have been developed can be used for constructing the various tables for the thermodynamic properties such as enthalpy, internal energy, and entropy using the known PVT data and any limited specific heat data. The technique that I showed very briefly was an integration technique. There is also methodology discussed in the text for using a differential technique, again using the same type of data. Okay, this next section we want to discuss another way to obtain enthalpy and entropy utilizing what are referred to as departure charts. And basically what departure charts are charts that are similar in design to compressibility charts, such that they are generated with respect to a reduced pressure and a reduced temperature, like the compressibility chart was, but it's to determine the real gas enthalpy or entropy based on the behavior of the gas as if it was an ideal gas as opposed to a real gas. And so the technique that's used in this particular case starts off with a description of the change in enthalpy between two thermodynamic points. And again, because we are dealing with a real gas, enthalpy may be a function of both temperature and pressure. Okay, for an ideal gas, we said one of the things that allowed us to solve or to use enthalpy was that for an ideal gas, enthalpy was only a function of the temperature of that thermodynamic state. But a real gas may have a pressure dependency. So if we were to look at the change of enthalpy between two thermodynamic state points, this particular change can be written or expanded out to include those values where we then subtract the ideal gas value for the enthalpy. And so the value of H star here, which is a function of only temperature, is the ideal gas value. So what we've done here on the right hand side is just added and subtracted H star to this equation here. We've done the same thing for H star evaluated at T1. And so basically we've taken this and we've added and subtracted, well, subtracted and added over here. So now what we have is we have an expression that says that the change in the enthalpy for a real gas between two states can be written as the change of the enthalpy, assuming that it was an ideal gas, only a function of temperature, and then this underlined term here. And so what we have in this underlined term is a bracketed amount that we are going to say is the departure of enthalpy with respect to the ideal conditions. So as you see here at state 2, given by temperature and pressure, this value right here is the actual value of enthalpy, where we then subtract the ideal gas value. And we do the same thing for state point 1. And so at state point 1, we determine the ideal gas value of enthalpy and subtract it from the real gas enthalpy at state 1. And so these, if you want to think of them, these are corrections or these are departures of the behavior with respect to the ideal gas behavior. And so how are these obtained? Well, those are obtained based on experimental data, and one can show that those differences, these departures, can then be written as an integral with respect to the change in pressure. Okay, and so again, in the textbook, they show you how that is done and what is actually happening there. And so if we have, for a real gas, if we have this behavior, this volume, temperature, pressure behavior, and we establish a zero reference point, and we perform this integration, we then can obtain the actual departure of the enthalpy with respect to the ideal gas behavior. Another way of thinking about it is that since we're referencing this at zero pressure, the enthalpy is, we would consider the enthalpy to be the ideal gas enthalpy. And so those starred conditions then can be obtained in this particular fashion. And so in order to utilize this departure, it's convenient to take the departure value and to normalize it by dividing it by RTC. And again, R bar is the universal gas constant, and TC is the critical temperature for that particular substance. And so when one does that, one then has an enthalpy departure that is non-dimensional. And so by dividing the enthalpy value by the RTC value, we then non-dimensionalize this departure value, so that all we have to do then is to perform the integration, the pressure integration, over a range of reduced pressures and reduced temperatures. And so we can show that what we had before, this right here, can actually then be related to the behavior of the compressibility factor. Okay, and so since we have this compressibility factor information, we can then perform this integration and develop then an enthalpy departure function. And so then, if we are then interested in the actual change in the enthalpy between two states, all we now have to do is take the ideal gas change, which is only a function of temperature between the two states, and then we correct it by looking into the departure charts for these two values. And again, these two values are the departure of the actual enthalpy with respect to the ideal gas enthalpy. You'll notice that in this particular case, the starred condition and the real condition have just been switched, the negative sign. And so one is, the departure of the ideal gas minus the real. So in this particular case, we had the real minus the ideal, and all they've done is just switch them. And so we have made it such that it's just a sign change. And so one now can determine the actual enthalpy change by looking at charts for this value and this value, knowing how the enthalpy changes between two temperature points for the ideal gas, and then do this correction. Now the same thing holds for entropy. And entropy, we already knew that entropy was a function of both temperature and pressure. but a real gas entropy change between a state point temperature pressure and another state point temperature and pressure can be written, as we've done before, as the ideal gas change. And again, ideal gas is a function of temperature and pressure, and we've seen equations that we've been able to use to determine the ideal gas entropy change. And then we have the corresponding departure values for the entropy. And again, that change of the actual entropy versus the ideal gas entropy can be shown to be related to a similar type of an expression and integration with known data. And now that known data can be obtained from the compressibility chart. And so as we look at this integral here, it can be shown that it's directly related to the compressibility as a function of the reduced pressure. What has happened now again is we've seen that the entropy departure has been non-dimensionalized. And so by dividing this by R, we now have, since entropy has the same units as R, we then see that this is a non-dimensional value here, and we can show that this particular non-dimensional value for entropy is directly related to the non-dimensional change in the enthalpy as well as that integral term. And so we can now, since this is the departure for entropy, we now can have an expression that says the actual change in the entropy can be shown to be related to the ideal gas change minus, and then again, our departure charts will give us this value and this value. And so this is basically then going to be the correction for the change of entropy with respect to the change of entropy if it had been an ideal gas. And so in the textbook, there are a couple of examples of showing how one can use the departure charts for enthalpy as well as for entropy to look at the work that's developed in a turbine. And again, instead of just assuming ideal gas enthalpy change, which represents the work of the turbine, we now have a real gas change of enthalpy representing the work of the turbine. Likewise, in this example, the turbine, if entropy is being generated in the turbine, we recognize that that's a source of irreversibility. Now, prior to this time, we always evaluated the entropy as an ideal gas. And so in this particular problem, the entropy change or production then is for a real gas reference to that of an ideal gas in order to solve this. And so these two problems utilize real gas behavior. So let's finish up on this particular section by just referring or referencing the departure charts for enthalpy and entropy. And prior to doing that, I want to remind you of the compressibility charts, the Z chart, as a function of reduced pressure and reduced temperature. And again, this was information that's in the back of your textbook, in the textbook itself, as the generalized compressibility chart. And again, this was if you knew the pressure of the gas, you could then determine its reduced pressure by dividing it by its corresponding critical pressure. Likewise, if you knew the temperature of the gas, you can determine its reduced temperature by dividing by the value of the critical temperature, and upon those two values you then can determine what is the compressibility. And so the compressibility is basically PV over RT. If the compressibility is equal to 1, we know that it's behaving as if it was an ideal gas. And if it departs from 1, we know that it is behaving at some percentage of what an ideal gas would be doing. Either could be a compressibility factor lower than 1 or a compressibility higher than 1. And so we have this, the chart kind of splits off here in order to show at higher temperatures we see the compressibility is above 1. Now with that compressibility chart, this also expands. What we're seeing here is this section right here, where we went from a reduced pressure from 0 to 10 and some reduced temperatures. This chart here is looking at very high pressures, higher values of reduced pressure, and again, as you can see, different values of reduced temperature, and how the compressibility factor is above 1 for those very high pressures. And again, when I say high pressure, it's for a pure substance whose pressure is a certain fractional higher than its critical pressure. And the same thing holds for the temperature. And so now this is the result of using the compressibility and coming up with what we refer to as the departure chart for enthalpy. And so the axes, again, let me see if I can reduce. Okay. Can't get rid of my, oops, sorry. Okay. Okay, I can't get rid of my menu bar here for a second, so unless I do this. Oh, there we go. Okay, so I made it smaller. And so the axes here are the similar to what we had before. Here is the reduced pressure, the P sub R, and then over here are the reduced temperatures, lines of constant reduced temperature, and the y-axis now is that departure relationship. And again, it is written as the ideal gas minus the actual enthalpy. So what you see is for most cases, okay, this departure value is a positive number, greater than 0. And so what that tells is that it's at these conditions given here, we see that the actual enthalpy is less than the ideal gas enthalpy, unless this is equal to 0. And so only for these cases over here where we have reduced pressures, and so if we were in the superheated region for a gas below the critical pressure, and if our temperatures were such, we would be in this region here where this, we would say that the ideal gas behavior is appropriate. But for any other higher pressures at temperatures above the critical pressures, and that's what we're seeing here, is T sub R's that are, 1 above 1 up to 4 here. And with those, we then see that this correction factor, this departure, takes on a certain value. And again, that departure is relative to the RTC value. And then a similar chart can be obtained for the departure of entropy. And so we're comparing the ideal gas entropy to the real gas entropy, normalizing it or non-dimensionalizing that difference by the R so that there are no units on this. And so we then see for a given reduced pressure and a given reduced temperature, we then are able to determine what that particular value is. And so what happens then is we can come back up here and we then say, okay, let's say we were doing this problem here, entropy change through the turbine. And so once we went from the incoming to the outgoing condition, we wanted to know the change in the entropy. And the change in the entropy would be given by the ideal gas change, and that would just be related to change in temperature, change in pressure, a lot of those equations that we saw earlier in chapter 6. But then what happens is we would go into our departure charts to determine this value for the incoming condition 1, this value for the incoming condition, the outgoing condition 2, take the difference, multiply it by R bar, and then that is how we correct the ideal gas value. Likewise, if we were doing the enthalpy to determine the work, we would determine the incoming and the outgoing condition. We then would say, okay, based on ideal gas behavior, we have a certain amount of work due to this change in ideal gas enthalpy. But then we go to the charts, the real charts, and we were able to determine then the departure on enthalpy, based on the incoming and the outgoing condition. We take the difference, we multiply it by RTC to get it into the appropriate units of enthalpy, and we then subtract that change from the ideal gas value. And so our next video then will be using the test software to actually look at real gas behavior. And as we look at real gas behavior, we'll see that the test software will allow us to put in a temperature and a pressure for a substance, and it will calculate, based on this chart, it will calculate the compressibility factor. And so the compressibility factor will give us an idea of whether or not the substance is going to behave as an ideal gas or a real gas. And then once we determine that, we'll see that it can also calculate the departure values for the enthalpy and for the entropy. And again, that can tell us how much it's going to depart from ideal gas behavior. And so with that, we'll stop this video and we'll take a look at what the software can do for us.